So this short video is going to be a brief explanation of the geometric interpretation of directional derivatives. So our starting point is thinking of an affine space as merely a mathematical set of points. So each point in this space will be given its own mathematical identity, and we are at this point not yet connecting to a coordinate description. We'll do this in a second. So we're going to think of points in this space as sort of places that we can visit, and we're going to think of vectors as directions that we can move away from points, and directions that tell us how to connect two different points. Okay? So that's going to be our basic setup. So in this context, a function will be an assignment of real values. So let's draw the axis R here to each point of our affine space. Okay, let's call our affine space S if you want. So the basic idea here is that if I specify a vector direction u from a point P, the entire direction is drawn by generating other affine space points xt given by the following expression: xt equals p plus an arbitrary parameter value times our direction vector. Okay, where these p and x are our notation for points in the affine space S. Okay, so the one thing I want to remind you is that in conventional single variable calculus, when we have two variables, t and s, and some dependence between them, the instantaneous rate of change at a specific value here is given precisely by the derivative once s is specified by some dependence on the parameter t. So we say here that the instantaneous rate of change is given by this expression, by the derivative. Okay, so what we're going to do is to essentially recover this familiar situation in the case of an affine space and a direction determined by a vector u. So if we imagine now the axis of parameter values, the curve xt will be the curve assigning points in this way. And so you can imagine that by changing my parameter values t, I go into S, my space, where I assign to each point a function f, and then that takes me to my axis R, where, you know, if I combine the two, I encounter a composition that I call basically G of t, which is made of f composed with x of t. Okay? So it is now this function g that we can interpret as our ordinary single variable function here. And so if we want to ask the function f, what is your rate of change instantaneously in the direction of u, we simply compute the derivative of g of t at t equals 0. Why t equals 0? Because for the parameter value t equals 0, this expression becomes p. And so that recovers the information that we want. If we go to a different point p, then we'll need a different expression for that particular direction. And so the directional derivative is going to be specified by the direction of u of the function f evaluated at the point p. And this is by definition the derivative of the function g that we are defining as this composition with respect to my parameter evaluated at 0. So what we are doing is we are first going from our parameter axis t into our space, then mapping with f, right? And the idea here is that the parameter value 0 corresponds to the point P. And so that's why we set our derivative of g with respect to t at the value 0. So if we now introduce a set of coordinate axes, x and y, then suddenly our points are given by pairs of real numbers. So we attribute coordinates to each of our points in the affine space. So this point we'll call x0, y0. And then some arbitrary point here along the direction specified by u will be given by some x of t and y of t. And so if our vector u is expressed in the standard basis determined by the axis x and y in the following form, so if we call this, for example, I and j, as you're familiar with, then our vector u will be some pair of arbitrary coefficients times I plus b times j. Okay? So what that means is that we can write our coordinates xt, yt more explicitly as x0 plus ta, y0 plus tb. And so our function g, which is just the composition of f with x of t, becomes an explicitly single variable dependent function. So it becomes g of t simply given by f, which now will have two entries, and the first entry will be x0 plus ta, second entry will be y0 plus tb, and then of course y0 and a are sort of fixed data, and therefore the only dependence that we see explicitly is with t. Now, just by applying directly this definition of directional derivative, we will recover the notation and definition given in the slides. So now the information is the same. I have some vector u, I have function f. Now the point is of course specified by the coordinates that our coordinate axis give, and well, we'll just proceed systematically at 0. So what I write down here is just the definition of derivative as from your single variable calculus classes. So what I would write is the limit for some auxiliary parameter delta of g of 0 plus delta, so in this case is delta, minus g of 0 over delta, this is just the common definition of derivative. And now of course delta g is given by this expression, so you can directly compare this to the slides and check that indeed we recover the same expression, y0 plus delta b minus f of x0 y0 over delta, and that should be the formula that you find in the slides. So in summary, we've seen that the directional derivative is the answer to the question for a function that asks what is the rate of change in a particular direction u. So we have this geometric data, which is a point and a direction, and when we identify our function with a smooth assignment of real values to points in our space, we can basically answer that question by doing this definition and just sort of using our knowledge from elementary calculus.